The light emitting diode, LED, is today's most energy efficient and rapidly developing lighting technology. Quality LED light bulbs last longer, are more durable, and offer comparable or better light quality than other types of lighting. LED is a highly energy efficient lighting technology, and has the potential to fundamentally change the future of lighting in the United States. Residential LEDs, especially Energy Star rated products, use at least 75% less energy, and last up to 25 times longer, than incandescent lighting. Widespread use of LED lighting has a large potential impact on energy savings in the United States. By 2035, the majority of lighting installations are anticipated to use LED technology, and energy savings from LED lighting could top 569 TWh annually by 2035, equal to the annual energy output of more than 92 1000 MW power plants. LED lighting is very different from other lighting types such as incandescent and CFL. Key differences include: light source. LEDs are the size of a fleck of pepper, and can emit light in a range of colors. A mix of red, green, and blue LEDs is sometimes used to make white light. Direction. LEDs emit light in a specific direction, reducing the need for reflectors and diffusers that can trap light. This feature makes LEDs more efficient for many uses such as recessed downlights and task lighting. With other types of lighting, the light must be reflected to the desired direction, and more than half of the light may never leave the fixture. Heat. LEDs emit very little heat. In comparison, incandescent bulbs release 90% of their energy as heat, and CFLs release about 80% of their energy as heat. Lifetime. LED lighting products typically last much longer than other lighting types. A good quality LED bulb can last 3 to 5 times longer than a CFL and 30 times longer than an incandescent bulb. LED lighting is available in a wide variety of home and industrial products, and the list is growing every year. The rapid development of LED technology has resulted in increased product availability, improved manufacturing efficiency, and lower prices. Below are some of the most common types of LED products. The high efficiency and directional nature of LEDs makes them ideal for many industrial uses. LEDs are increasingly common in street lights, parking garage lighting, walkway and other outdoor area lighting, refrigerated case lighting, modular lighting, and task lighting. Because LEDs are small and directional, they are ideal for lighting tight spaces such as countertops for cooking and reading recipes. Since there can be variation in light color and directionality, it is important to compare products to find the best fixture for your space. Recessed downlights are commonly used in residential kitchens, hallways, and bathrooms, and in a number of office and commercial settings. DOE estimates there are more than 600 million recessed downlights installed in U.S. homes and businesses. With performance improvements and dropping prices, LED lamps can affordably and effectively replace 40, 60, 75, and even 100-watt incandescent bulbs. It's important to read the lighting facts label to make sure the product is the right brightness and color for its intended use and location. LEDs consume far less electricity than incandescent bulbs, and decorative LED light strings such as Christmas tree lights are no different. Not only do LED holiday lights consume less electricity, they also have the following advantages. Safer. LEDs are much cooler than incandescent lights, reducing the risk of combustion or burnt fingers. Sturdier. LEDs are made with epoxy lenses, not glass, and are much more resistant to breakage. Longer lasting. The same LED string could still be in use 40 holiday seasons from now. Easier to install. Up to 25 strings of LEDs can be connected end-to-end without overloading a wall socket. LED stands for Light Emitting Diode. LED lighting products produce light up to 90% more efficiently than incandescent light bulbs. How do they work? An electrical current passes through a microchip, which illuminates the tiny light sources we call LEDs, and the result is visible light. To prevent performance issues, the heat LEDs produce is absorbed into a heat sink. The useful life of LED lighting products is defined differently than that of other light sources. such as incandescent or compact fluorescent lighting, CFL. LEDs typically do not burn out or fail. Instead, they experience lumen depreciation, wherein the brightness of the LED dims slowly over time. Unlike incandescent bulbs, LED lifetime is established on a prediction of when the light output decreases by 30%. LEDs are incorporated into bulbs and fixtures for general lighting applications. Small in size, LEDs provide unique design opportunities. Some LED bulb solutions may physically resemble familiar light bulbs and better match the appearance of traditional light bulbs. Some LED light fixtures may have LEDs built in as a permanent light source. There are also hybrid approaches where a non-traditional bulb or replaceable light source format is used and specially designed for a unique fixture. LEDs offer a tremendous opportunity for innovation in lighting form factors and fit a wider breadth of applications than traditional lighting technology. LEDs use heat sinks to absorb the heat produced by the LED and dissipate it into the surrounding environment. This keeps LEDs from overheating and burning out. Thermal management is generally the single most important factor in the successful performance of an LED over its lifetime. The higher the temperature at which the LEDs are operated, the more quickly the light will degrade, and the shorter the useful life will be. LED products use a variety of unique heat sink designs and configurations to manage heat. Today, advancements in materials have allowed manufacturers to design LED bulbs that match the shapes and sizes of traditional incandescent bulbs. Regardless of the heat sink design, all LED products that have earned the Energy Star have been tested to ensure that they properly manage the heat so that the light output is properly maintained through the end of its rated life. LED lighting differs from incandescent and fluorescent in several ways. When designed well, LED lighting is more efficient, versatile, and lasts longer. LEDs are directional light sources, which means they emit light in a specific direction, unlike incandescent and CFL, which emit light and heat in all directions. That means LEDs are able to use light and energy more efficiently in a multitude of applications. However, it also means that sophisticated engineering is needed to produce an LED light bulb that shines light in every direction. Common LED colors include amber, red, green, and blue. To produce white light, different color LEDs are combined or covered with a phosphor material that converts the color of the light to a familiar white light used in homes. Phosphor is a yellowish material that covers some LEDs. Colored LEDs are widely used as signal lights and indicator lights, like the power button on a computer. In a CFL, an electric current flows between electrodes at each end of a tube containing gases. This reaction produces ultraviolet, UV, light and heat. The UV light is transformed into visible light when it strikes a phosphor coating on the inside of the bulb. Incandescent bulbs produce light using electricity to heat a metal filament until it becomes white hot or is said to incandesce. As a result, incandescent bulbs release 90% of their energy as heat. LED, in electronics, a semiconductor device that emits infrared or visible light when charged with an electric current. Visible LEDs are used in many electronic devices as indicator lamps, in automobiles as rear window and brake lights, and on billboards and signs as alphanumeric displays or even full-color posters. Infrared LEDs are employed in autofocus cameras and television remote controls and also as light sources in fiber optic telecommunication systems. The familiar light bulb gives off light through incandescence, a phenomenon in which the heating of a wire filament by an electric current causes the wire to emit photons, the basic energy packets of light. LEDs operate by electroluminescence, a phenomenon in which the emission of photons is caused by electronic excitation of a material. The material used most often in LEDs is gallium arsenide, though there are many variations on this basic compound, such as aluminum gallium arsenide or aluminum gallium indium phosphide. These compounds are members of the so-called 3V group of semiconductors, that is, compounds made of elements listed in columns 3 and V of the periodic table. By varying the precise composition of the semiconductor, the wavelength, and therefore the color, of the emitted light can be changed. LED emission is generally in the visible part of the spectrum, i.e., with wavelengths from 0.4 to 0.7 micrometer, or in the near infrared, with wavelengths between 0.7 and 2.0 micrometers. The brightness of the light observed from an LED depends on the power emitted by the LED and on the relative sensitivity of the eye at the emitted wavelength. Maximum sensitivity occurs at 0.555 micrometer, which is in the yellow, orange and green region. The applied voltage in most LEDs is quite low, in the region of 2.0 volts. The current depends on the application and ranges from a few milliamperes to several hundred milliamperes. The term diode refers to the twin-terminal structure of the light-emitting device. In a flashlight, for example, a wire filament is connected to a battery through two terminals, one, the anode, bearing the negative electric charge, and the other, the cathode, bearing the positive charge. In LEDs, as in other semiconductor devices such as transistors, the terminals are actually two semiconductor materials of different composition and electronic properties brought together to form a junction. In one material, the negative, or N-type, semiconductor, the charge carriers are electrons, and in the other, the positive, or P-type, semiconductor, the charge carriers are holes created by the absence of electrons. Under the influence of an electric field, supplied by a battery, for instance, when the LED is switched on, current can be made to flow across the PN junction, providing the electronic excitation that causes the material to luminesce. In a typical LED structure, the clear epoxy dome serves as a structural element to hold the lead frame together, as a lens to focus the light, and as a refractive index match to permit more light to escape from the LED chip. The chip, typically 250 times 250 times 250 micrometers in dimension, is mounted in a reflecting cup formed in the lead frame. The PN-type gap N layers represent nitrogen added to gallium phosphide to give green emission, the PN-type GaS-PN layers represent nitrogen added to gallium arsenide phosphide to give orange and yellow emission, and the P-type gap ZNO layer represents zinc and oxygen added to gallium phosphide to give red emission. Two further enhancements, developed in the 1990s, are LEDs based on aluminum gallium indium phosphide, which emit light efficiently from green to red-orange, and also blue-emitting LEDs based on silicon carbide or gallium nitride. Blue LEDs can be combined on a cluster with other LEDs to give all colors, including white, for full-color moving displays. Any LED can be used as a light source for a short-range fiber optic transmission system, that is, over a distance of less than 100 meters, 330 feet. For long-range fiber optics, however, the emission properties of the light source are selected to match the transmission properties of the optical fiber, and in this case the infrared LEDs are a better match than the visible light LEDs. Glass optical fibers suffer their lowest transmission losses in the infrared region at wavelengths of 1.3 and 1.55 micrometers. To match these transmission properties, LEDs are employed that are made of gallium indium arsenide phosphide layered on a substrate of indium phosphide. The exact composition of the material may be adjusted to emit energy precisely at 1.3 or 1.55 micrometers. An LED lamp or LED light is an electric light that produces light using light-emitting diodes, LEDs. LED lamps are significantly more energy efficient than equivalent incandescent lamps and fluorescent lamps. The most efficient commercially available LED lamps have efficiencies exceeding 200 lumens per watt, LM/W, and convert more than half the input power into light. Commercial LED lamps have a lifespan several times longer than both incandescent and fluorescent lamps. LED lamps require an electronic LED circuit to operate from mains power lines, and losses from this circuit means that the efficiency of the lamp is lower than the efficiency of the LED chips it uses. The driver circuit may require special features to be compatible with lamp dimmers intended for use on incandescent lamps. Generally, the current waveform contains some amount of distortion, depending on the luminaire's technology. LEDs come to full brightness immediately with no warm-up delay. Frequent switching on and off does not reduce life expectancy as with fluorescent lighting. Light output decreases gradually over the lifetime of the LED. Some LED lamps are drop-in replacements for incandescent or fluorescent lamps. LED lamps may use multiple LED packages for improved light dispersal, heat dissipation, and overall cost. The text on retail LED lamp packaging may show the light output in lumens, the power consumption in watts, the color temperature in kelvins, or a color description such as warm white, cool white, or daylight, the operating temperature range, whether the lamp is dimmer compatible, whether the lamp is suitable for humid/damp/wet conditions, and sometimes the equivalent wattage of an incandescent lamp delivering the same output in lumens. LED lamps are used for both general and special purpose lighting. Where colored light is needed, LEDs that inherently emit light of a single color require no energy-absorbing filters. LED lamps are commonly available as drop-in replacements for either bulbs or fixtures, replacing either an entire fixture, such as LED light panels replacing fluorescent troffers, or LED spotlight fixtures replacing similar halogen fixtures, or bulbs, such as LED tubes replacing fluorescent tubes inside troffers, or LED HID replacement lamps replacing HID bulbs inside HID fixtures. The differences between replacing a fixture and replacing a bulb are that, when a fixture, like a troffer, is replaced with something like an LED panel, the panel must be replaced in its entirety if the LEDs or the driver it contains fail, since it is impossible to replace them individually in a practical fashion, although the driver is often separate and so it may be replaced, whereas, if only the bulb is replaced with an LED replacement lamp, the lamp can be replaced independently of the fixture should the lamp fail. Some LED replacement lamps require the fixture to be modified, such as by electrically removing the fixture's ballast, thus connecting the LED lamp directly to the main supply. Others can work without any modifications to the fixture. White light LED lamps have longer life expectancy and higher efficiency, more light for the same electricity, than most other lighting when used at the proper temperature. LED sources are compact, which gives flexibility in designing lighting fixtures and good control over the distribution of light with small reflectors or lenses. Because of the small size of LEDs, control of the spatial distribution of illumination is extremely flexible, and the light output and spatial distribution of an LED array can be controlled with no efficiency loss. LEDs using the color mixing principle can emit a wide range of colors by changing the proportions of light generated in each primary color. This allows full color mixing in lamps with LEDs of different colors. Unlike other lighting technologies, LED emission tends to be directional, or at least Lamarckian, which can be either advantageous or disadvantageous, depending on requirements. For applications where non-directional light is required, either a diffuser is used, or multiple individual LED emitters are used to emit in different directions. LED emitters are inherently suitable for dimming, because they can operate over a wide range of currents without significant change of color. However, the circuits in LED lamps must be explicitly designed to be dimmable and compatible with particular types of dimmer switch. Otherwise, damage to the lamp or the dimmer may result. Color rendering is not identical to that of incandescent lamps, which emit close to perfect blackbody radiation, as does the sun. A measurement unit called CRI is used to record how a light source renders 8 color sample chips, on a scale from 0 to 100. LEDs with CRI below 75 are not recommended for use in indoor lighting. Badly designed LED lamps may flicker. The effect can be seen on a slow-motion video of such a lamp. The extent of flicker is based on the quality of the DC power supply built into the lamp structure, usually located in the lamp base. Longer exposures to flickering light contribute to headaches and eye strain. LED lifespan as a function of lumen maintenance drops at higher temperatures. Thermal management of high-power LEDs is a significant factor in design of solid-state lighting equipment. LED lamps are sensitive to excessive heat, like most solid-state electronic components. Also, the presence of incompatible volatile organic compounds can impair the performance and reduce lifetime. The long life of LEDs, expected to be about 50 times that of the most common incandescent lamps and significantly longer than fluorescent types, is advantageous for users but will affect manufacturers as it reduces the market for replacements in the distant future. The human circadian rhythm can be affected by light sources. The effective color temperature of daylight is 5,700 K, bluish-white, while tungsten lamps are 2,700 K, yellow. People who have circadian rhythm sleep disorders are sometimes treated with light therapy, exposure to intense bluish-white light during the day, and dark therapy, wearing amber-tinted goggles at night to reduce bluish light. Some organizations recommend that people should not use bluish-white lamps at night. The American Medical Association argues against using bluish-white LEDs for municipal street lighting. Research suggests that the shift to LED street lighting attracts 48% more flying insects than HPS lamps, which could cause direct ecological impacts as well as indirect impacts such as attracting more gypsy moths to port areas. Thank you for watching this video.